Hello again, guys. So continuing with the same problem that we had before, now we're gonna go and do the part D. The part D, it was the influence line for the moment at the point C. So we had the same drawing that we had before. I should have drawn this before, but some students, some viewers asked me to do the drawing with me because that introduces them to the topic, but this is already introduced a long time ago. So By 444, 4 meters, 4 meters, 4 meters, and this is the point C. And then we calculated before in the previous part, we calculated the reaction at Y. If we have a moving load somewhere, moving load of 1 with the distance x, we calculated that AY 1 minus 1/8 of x. We did that in the previous video. But if you want to do it, it's simple. So you do summation of moments at B equals 0. So negative AY times 8, and then plus 1 multiplied by 8 minus x. And then solve for that, and that's going to give you the value for AY. And we already said also that the situation here at the point C is changing because the moment at C is the one that I'm being asked to calculate. And if you remember, or if you even if you don't remember, we just saw it right in the other video. So you're gonna have here your reaction AY, and you have to make a cut at the point C. And this is what is happening here. So you have By here in this end, and the internal reactions, forces, and moments are V and M, and if you use this side, V and M at C. And once again, the shear is the same, the moment is the same also, no matter what you do. But we have to break it down in two parts. So the first part, it was between 0 and 4, and it's this part, when the load, the moving load, is in this part. This distance, we call it x, and this is 4. So this distance from here to here is going to be 4 minus x. If I want to calculate the moment, I'm going to do summation of moments at C equals 0. And if you do moment here, you're going to have negative AY times 4 plus this 4 minus x times 1 plus MC equals 0. So I'm going to pass everything that I have here to the other side. So if I pass this to the other side, then I'm going to have MC is negative 4AY minus, why negative 4AY? I don't know. I don't like writing these things the same day. My brain gets fried. So this is negative, and nobody told me anything again. I'm saying negative and negative and negative, and I'm putting positive. Summation of moments, rotation in this way, negative 4AY plus, this is correct. Now if I pass this to the other side, then I'm going to have positive 4AY minus 4 minus x, and I'm mad at me, not at you. Well, at you kind of, because you didn't tell me. But it was more difficult for you to tell me, right? So MC equals 4 times this, which is 1 minus 1/8 of x minus 4 minus x. Now MC is going to be equal to 4 minus 0.5x, or 1/2 x, minus 4 plus x. This and this cancel out. 1 minus 0.5 is 0.5. So 1/2 x, or 0.5 x. That's going to be the value of the moment when the load is from here to here. And this is the part that I was arguing in the last video about being easier or not easier. Now when the load is passing that point C, which is between 4 and 12, you have two options. Either you keep using these for your analysis, or then you use this for your analysis, because now the load is acting here and the load is not acting there, so you don't have that vertical load over there. Now what is the implication of that? Let's use the left side, which is the normal thing to do. If I use the left side, I come here and I say, okay, the summation of moments at C equals 0. Remember, I'm using this side. Equals 0. So you have negative 4ay, negative 4ay, negative 4ay, negative 4ay. There's no load here because now the load is in this side. Plus m equals 0. So nc is equal to negative 4ay, or nc is equal to negative 4 times 1 minus 1/8 of x, or nc equals 4 minus, pass it to the other side, right? 4 minus 1/2 of x. There you go. For this other side, if I use this side. Now, I didn't want too much to explain you that. But just for you to see what I'm trying to tell you is this. Now, there's not too much of a difference, but let's say that I want to use this side instead of using that side for calculating the moment between 0, 4, because you're already here, and 12 when the load is here. So remember, the x distance is being measured from here. So that distance is x at any point. And the distance from here to here is 4. So the distance from here to the load at any point is going to be x minus 4. That's going to be the distance. X minus 4. And if you do summation of moments at C equals 0, then you have what? You have negative 1 times x minus 4 plus this distance. How much is that distance? This distance is this, 4by, and nothing else except the moment, minus nc equals 0. Now mc will be equal to 4by plus x minus 4, passing everything, passing this to the other side, minus, I pass this to this side, so nc is 4by minus, yeah, I keep this in this side, pass this to the other side. And now I remember from, once again, last time, and we can do it, that when we calculated by was 1/8 of x. So I can come here and say, instead of by, 1/8 of x, so nc is 4 times 1/8 of x minus x plus 4, and nc is going to be, this is going to be 0.5 x minus x plus 4, or mc is going to be equal to 4 minus 0.5 x, or 1.5 x, which is the value that we got here in the same way that we did it before. Now, is this too much long? No. Wait until you have to do this in frames, for example, or in a different type of structures. This is going to be way longer. And what I don't understand is, why do we have to switch if I think it's simpler, you know, to do just this part. So both approaches are correct. I just wanted to show you this part, but don't get confused. Just go review it again. I'm going to keep using this, or this is the same. And now we just have to build the table for doing this. Now, what is the table going to look like? Like the same tables that we did before. But now it's going to be moment. So I'm going to have what? I'm going to have x and the moment at C. In the case of the moment, I don't have to, but anyway, I'm going to do it just to show you what happened. 1, 2, 0, 4 from this side, 4 from this side, 8 and 12 and 12. Remember, when you are in this interval, you have to use the first equation that we got, this equation, 1/2 of x And when you are in this other interval, you have to use this other equation because it's between 4 and 12. So this is 4 minus 1/2 of x. Now let's do that. When you put 0 here, this is 0. If you put 4 in here, this is gonna be what? This is gonna be 1/2 of 4 is 2. Now if I use this equation, which is this part, and I put 4 in this equation, it will be 4 minus 1/2 of 4, which is 2. And following with this equation, if I put 8 here, it will be 4 minus 1/2 of 8. This is 4 minus 4, 0. And if I put 12 here, it's going to be 4 minus 1/2 of 12. This is 6. 4 minus 6 is negative 2. Negative 2. So once you have that, I wanted to do it because I wanted to show you this. The moment doesn't change if you have a concentrated force applied at the same point, at that point. And we have been talking about this. However, remember the shear jump at that point. Now the last step is plot. An influence line is not an influence line until you have plotted it. So if we plot that, then you're going to have the moment at C. You're going to have the 4 meters. Other 4 meters here, so this is 4, this is 8, and this is 12. And this is x in meters. And now we plot these values. When this is 0, it's 0. When this is 0, this is going to be 2. What units? It's a moment. What units? No units. Remember that. No units. The reason we don't have any unit is because those are dimensionless. 2. Now when this is equal to 8, no, when it's 4 in the other side, it's also 2, it doesn't change. When it's equal to 8, it's 0, and when it's equal to 12, it's negative 2. Here, negative 2. And then you use your ruler. If I remember where it is, that would be awesome. If I don't remember where it is, it doesn't matter, I use anything. So there you go. I use that over there. Negative 2. This is positive, this is negative. Once again, remember what happened. Now you have to tell me, I'll be back, because I'm going too far away. Now you have to tell me, this is a bridge, for example. What is the maximum moment for design? You get your car or your concentrated load, and you put your concentrated load, whatever is going to produce what the maximum positive moment should be somewhere here, right? If you want to find the maximum negative effect, it will be somewhere here in this part. Now we're going to be discussing this really soon, but let's say that just for the sake of what if, I like to play the what if game. That's a really neat game. And I say, what if now you have this unit influence line for that, and now you have your beam, which we already have, is this, and this is the roller, and this is the pin that goes in this part. And what if now we did an analysis and we determined that we have a dead load of, I don't know, 5 kilonewton per meter, and we know there exists a concentrated live load of a concentrated distributed live load. I'm going to switch this just for 6 kilonewton per meter, and on top of that I have also a concentrated live load of, I don't know, 50 kilonewton, for saying any stupidity. And I need to determine what is the location, or what is the, in this beam, what is going to give me the worst case scenario. Once again, the answer is it depends, because you can have positive or you can have negative maximum moment. If this is the case that we have, there are different approaches and different ways. I don't want to solve that problem now. I just want to tell you, I have to place these loads in such a way that produces the maximum effect. Dead load. Where do you place the dead load? You don't have any choice. The dead load is the dead load. That is applied everywhere, and it's not going to be moving, and it has to be there. Dead load. But you can do something else about these two. Now, if what I'm looking is for a maximum positive moment effect, I see that this is the maximum positive influence area. Meaning, if I put the live load everywhere, this is going to counter my maximum moment, this part here. So what I have to do is placing my live load only in this portion. Only in this portion, like that. That's going to be the maximum live load, and not here. And on top of that, this concentrated load, I will be placing it where the maximum positive value is, which is at the point C, right there, at the point C. That's what is going to give me the maximum positive value. And how do you do that? Well, you can calculate the statics in here and calculate the moment at that point, and that will give it to you. But if you have the influence lines, you just, it's simple. You get this area multiplied by this load, and you get this area multiplied by this load, and this area negative multiplied by this load, and this concentrated load here multiplied by that too, and that's it. And at the map, and that will give you the maximum moment at that point. But this is a discussion for a different video. I just want to tell you why are you gonna do this and how you're gonna do it. If you're looking for the maximum negative moment, now the situation is similar. The dead load is the dead load. You don't have anything to do with that. You cannot change it. You cannot do anything whatsoever. So dead load will be there. But if I'm looking for a maximum negative effect of the moment, this part is the part where I'm going to place the live load for doing that study. And this number, which is the maximum negative number, is the one that I'm gonna, this location is the one that I'm gonna put my concentrated live load. And then I calculate this in the beam, and that will give me at C the maximum positive if I use this, or at C the maximum negative if I use this distribution of the loads. We're gonna learn how to do that, and we're going to have a bunch of other problems that we are going to be working with. See you next lecture, guys. Next video, I'm sorry, next study sets, or whatever you want to call it. Next nightmare for you. Keep learning. Thank you for watching. Thank you for learning. See you later.